Okay, friend. So thanks for joining me again. So you can hear me fine, I guess. Yeah. So today we're going to cover basically the first lecture of the course. Obviously, as I was mentioning, the topic is SAGD and NCG co-injection. So optimizing SAGD basically. And SAGD is a recovery scheme. It's a recovery scheme to produce heavy oil, produce bitumen, which is the heaviest basically hydrocarbon on Earth. Before we get into the technicals, I think for this lecture is really important to cover kind of the background to oil production in the world so you can understand where this production of SAGD fits in, right? The overall heavy oil production, the bitumen production. So you can kind of see the importance of the industry, what role it plays, and why it's important to optimize the assets that we're going to be talking about. So, first of all, Canada has almost 10% of world's oil reserves, while US, as you can see in this table, it has about 4% of oil reserves. You can see basically on a barrel perspective. So we have about 170 billion barrels of oil in situ. Now, majority of that oil is the oil sands that cannot be mined underground. So you have to use some kind of thermal techniques to recover that oil. From this table, you will also see that about over 50% of world's oil reserves are in the Middle East, right? So I would argue we don't directly compete with them, but they do have a very important role that when it comes to dictating the price of oil in the world. So here you can see a slide on total oil production from OPEC Plus and OPEC and non-OPEC participants. So basically, these entities, OPEC and OPEC Plus, they formed an alliance to, they call it basically the incentive there is to incentivize investment into the sector, right? And the idea here is that you will not have a country that will basically be overproducing, oversupplying products, hydrocarbons, and then the demand will decline because now you're essentially trading on the margin, and you could be in a position where it's just not worth investing towards future production. So you see in the slide that Saudi Arabia so this slide is from U.S. Energy Information Administration, so from 2023. So Saudi Arabia produced about 10.4 million barrels a day. So right now they curtailed that production, right? A little bit less. Russia plays an important role, so close to that 10 million barrels a day as well. And you can see the smaller countries all around it, right? So they all kind of form this alliance of OPEC members where they decide on the supply that's going to be coming out of these countries. Now, I think for the context, it's really important to understand that the quality of the oil that comes from these countries is very different from the oil that we're going to be talking about today and working on, which is bitumen, the heaviest oil on Earth. So this is a slide on monthly crude oil production from the United States from January 1920 to 2025. And what do you guys see? Let's see in the private chat in the comments there, what's happening around 2010 timeframe towards 2020. Can somebody type it in the chat in the comments? Let's have it more interactive. Why do you think we see this huge uplift there? Any guesses? I'll give you a hint. It goes with the word, no, not SAGD, no. Actually, in the United States, they don't use SAGD. They don't have the type of oil we have. It rhymes with revolution, not horizontals. This is a shale revolution, the ability to frack tight formations. And what you essentially see is that we go from about 5 million barrels a day with huge oil uplift to about 13.5 million barrels a day. So just think about this. In the previous slide, we talked about the alliance of OPEC, OPEC Plus, trying to producing their production. And trying to control supply demand, where they incentivize investment for future production. And all of a sudden, in this time frame, we have this big revolution in oil production. Do you guys think it's kind of game changing when it comes to the dynamics in the world, when it comes to supply demand, when it comes to price volatility? I think so. And what you see essentially from the 2010 to 2015 timeframe, huge uplift in oil production. Then we see a slowdown. What happened there is that OPEC organizations were not happy about this increase that we saw in 2010 to 2014, 2015, and they basically invoked through regulation overproduction of hydrocarbons, and that resulted in slight decline. But you can see that further investment was advanced to the assets in the Permian, especially, and we see huge uplift towards 13 million barrels a day. Now, right now, we live in a very interesting time, and that's an exciting time for you guys as future employees in the energy sector, because the Permian is doing something really interesting right now. And many arguing that they're actually plateauing because we haven't seen significant increase on that rate of change that you've seen from 2010, 2011 timeframe, which is kind of a positive for prices and stability and kind of working in the sector, where if you have a lot of volatility and reduced prices, you don't see much hiring and you see lots of layoffs. And that's kind of what took place in 2014, 2015. So in a way, I'm very excited for you guys that you're entering the sector in the right kind of time. By the way, whoever is listening to this recording in the future, this is first lecture for State Petroleum Engineering students at their capstone program. So I'm sharing this publicly. So hopefully, welcoming you to my world of basically teaching about this for the past 11 years. All right. So this is the rate of change, as you saw from the previous chart, going from about 2 million barrels a day in the biggest region where majority of the inventory was for fracking tight shale formations. And you can see a huge uplift from 2015 towards 2020 timeframe, going from 2 million barrels a day to about 5. You can see COVID resulted in slight decline, obviously big shock to the system. And then I copy pasted the slope to the previous slope, and now we're recovering from COVID. You can see production at the same rate with same uplifts going to 6 million barrels a day or so. Now, what's really interesting about what I talked about before is what's in that black rectangle there, which is kind of plateauing. You don't see that big rate of change. So now you hear Daniel Smith, which is Premier of Alberta, talking a lot about maybe increasing production for oil in Alberta as function of kind of future supply to the United States. So there's a lot of kind of discussions on that topic right now. Okay, so this is a slide that was shared with Giovanni Stonovo on X on Twitter. Here you can see Alberta oil production for this context. And what you see in the blue line is the crude oil production in Alberta is about 4.2 million barrels a day. So let's kind of go back and better understand that production. Permian by itself is about 6, Alberta 4.2, oil production in US north of 13, Saudi Arabia about 10, Russia close to 10. So is Alberta playing a big role in oil production globally? I would say so. And the type of oil you guys are going to be learning about today is about half of that, which is in situ thermal production. So in November, we had record of 4.197 million barrels in November, right? So that's Alberta oil production. Previous record was 4.187, and that's based on Alberta Energy Regulator. So you guys you're learning about thermal recovery schemes, that playing the biggest chunk of production in an asset in a country that plays an important role globally in providing oil production. By the way, Deep, can you do a thumbs up if you can hear me okay? Because this is like totally random, spontaneous. Or anybody on that space there? Yeah, all good? Okay, awesome. Now, not all assets, not all regions increase production. What you can see here is Saskatchewan, total oil production is at the peak, it was 2.5 million barrels, right? Sorry, I'm lying. 2.5 million cubes annually, which translates to about. So how would you do it? Let's write in the comments. How would you calculate now the daily production based on this number? So here in the private chat, I will type 2,500,000 cubes per year. What would that equal in barrels per day? Let's take a look. Sorry, I added another zero. So obviously you divide by 365 to cube per day, right? Times 6.29 to get to barrel. So what's the answer? That's based on Ministry of Energy and Resources. We're going to get close to 40,000. What do you guys think? 43,000. That's right. So there are actually a lot of plans. Good job, John. So there's lots of plans to improve that production, increase it. I'm pretty sure this number is much higher right now, mostly from Lloyd thermal assets that are being optimized. And you guys gonna, it's part of your project. There will be some assets for some of your teammates or you yourself um, that will work on optimization of Lloyd thermal assets. So those will be smaller kind of scale SAGD operations, but you will be also kind of seeing some of those. Okay, next slide. So now let's kind of wrap it up in a little bit of a summary. So hydrocarbons are not like milk, right? Hydrocarbons, there is significant partitioning, and there's no one way to basically classify oil. For example, if you have a vapor pressure condition, like let's say you go to Costco and you get propane from a bullet, would that propane be in liquid phase or gaseous phase? It will be in liquid phase. It doesn't make sense to store it in gaseous phase because you'll need the entire Costco then to store it in that phase, right? You need the entire building. Where if it's in liquid phase, you can kind of compress it. So what we see here is that essentially production in US, it's over 13 and a half. But what I'm seeing here is that a Canadian Canadian Association of Petroleum Producers, they kind of count more liquids, I guess, partitioning. So you can see over closer to 17 there. Then Saudi, you see about 11. We saw it's maybe like 10 right now, maybe less, 9.5 or so, especially with curtailment. Russia is an important player. We are Canada, so just north of 5 million barrels. By the way, majority of it, I think over 4 million barrels is oil sands, right? And half of it will be, or close to a half will be thermal oil sands. The heavy oil partitioning is also happening there. And you also have the mining, which is something we're not going to be doing in this course. So this is more like shoveling, like you get trucks and they pick up the oil and treat it, right? And then we have Iraq, China, UAE, Iran, Brazil, Kuwait, around that like 3 to I would say 5 million mark. So about 95% of Canada oil production and all current natural gas production occurs in Western Canadian Sedimentary Basin. It's called WCSB, which spans provinces of British Columbia, Alberta, and Saskatchewan. And we do have Manitoba oil, some in Manitoba, very little though. And oil is also produced offshore, Newfoundland and Labrador as well, but very little on relative basis. When it comes to natural gas, 18.3 billion cubic feet, so 18.3 BCF 2024. And year-to-date average Canadian oil production 5.7 million based on that, but I think it's kind of much less. I think they calculate a little bit more with maybe NGLs, natural gas liquids, and kind of add those as well. What they do share here is that oil sands production is 3.3 million. So out of that, you would say, like, let's say it's 4 million heavy oil. So you get kind of to that, the delta between 3.3 to 4, more the heavy oils. And I would say about 1.8, 1.9 or so is the thermal stuff. So what we're going to be talking about. And other stuff is mining. You get some conventional production at 1.5 million. Again, what is oil? How do you count it? Do you get the NGLs, natural gas liquids, or is it just dry gas, right? Like, it's a little bit nuanced there, but that's how they basically classify it in here, which is why it explains why U.S. production is more elevated here from what I was showing previously. So here's the top 10 heavy oil producers in the world. This is more relevant to what we're doing. You can see nobody is even close to Canadian production when it comes to heavy oil on global scale. The closest one is China, so close to 1 million barrels a day, which is, by the way, a huge benefit to us because they will build refineries that are designed for heavier oils, sour kind of heavy oil type, not lighter ends, right? Not light stuff. So that really benefits Canadian production because now we can potentially treat our oil in their refineries. So this is kind of one of those big conversations right now in Canada about not having just one customer, which is United States, and basically going to West Coast and ship our oil overseas, so broadening our markets a little bit. Then you can see here on the slide Brazil as well. They do have some heavy oil production. Mexico. Mexico has been a little controversial lately because their production is kind of being kept in the country in a sense, right? But they do compete with us. Venezuela, many people speculate on that production replacing our production, which is, by the way, in a way, it's a blessing because in 1970s, when everybody were getting along, American refineries were designed for Venezuelan crude because remember in the slide we looked at the production in the United States. So look at 1970s, right? It's kind of ramping up towards 8 million barrels per day, plateauing, and then you see significant decline. And so those refineries were basically getting built for Venezuelan oil to be produced. And as the demand was increasing, but now you can see there, based on this slide, 500,000, maybe I think it's closer to 900,000 barrels a day right now. But again, Canada is by far the leader in that space. So the project will be basically related to this type of oil. Okay, this is a cute slide. What do you guys see here? We see some dogs. We see a gentleman. This is from 1920s. So first, when there was this realization about, oil, bitumen being basically utilized as oil, right? And how do you separate the sand, the water, the clays from the oil itself? They did some tests and basically loaded these dogs with like bags, put it on the dogs and transferred them, which is kind of cool. So we came a long way in the past 100 years, right? To our significant network here of pipelines between our two countries, United States and Canada. And it's kind of funny to reflect back in 1924. You see like dogs packed with oil sand samples. And I think one of you guys were mentioning about your passion working in kind of the lab environment and more kind of testing environment. And they would kind of sample the type of hydrocarbons, all the samples in the lab environment, and really understand the development in the 1920s, late 1920s. There was a big breakthrough with Dr. Clark in the University of Alberta in Edmonton, where they realized that now retrospectively it looks pretty simple, but that you could actually mix that tar, right, the oil, the hard oil, with water and separate the two, which is great, right? It gives you this opportunity to kind of create this new product. By the way, I don't see you guys, but whoever students are joining us right now, this is SAGD Petroleum Engineering capstone program lecture for the students, and we're just covering um, the first slides here, talking about our project and what kind of things, activities we're going to be doing in the next couple of months, 3-4 months, not couple of months. So here's a map of WCSB. So we talked about the Western Canadian Sedimentary Basin. Obviously, you can see here that Canadian oil is Alberta oil. So we're in the right province to be working on this project right now. You can see over 170 billion barrels in situ, proven reserves, and really lots of oil Alberta and Saskatchewan. So that's the map. So let's talk a little bit about the partitioning within the broader ecosystem on a cumulative basis. Where do we see the surface mining stuff, which is the blue line, and in situ, which is what we're working on. So you can see on the right scale there, close to 1.8 million barrels or so are being mined, and just as much being produced in situ. So we're actually in a very focal year right now, 2024, 2025, where the thermal production is actually going to be start surpassing the mining production, right? And again, it has something to do with inventories. Majority of those reserves are in situ, so they're very difficult to mine, impossible to mine, and you have to use thermal techniques to recover that oil. You cannot just go with giant trucks and to basically mine even, I would say, 50 meters underground. And just think about this: the assets we're going to be talking about, they all of them basically at about 200 meters to, I would say, about 450 meters underground. So at that level, between 200 to 450. Now think about the scale of that. In the room where you sit in the lab there, right? In our lab that we're going to be meeting there in 2 weeks, the height of the ceiling is, I would say, what is it, like 2.5, 3 meters? What would you say? So we're talking 200, 400 meters underground. So try mining for that without, injecting steam. Very difficult. It's very uneconomic. But also, the pressures in those conditions are extreme. For example, the pressure you feel right now on your skin is about 100 kPa, right? So 100 kPa. The pressure in your tire is going to be like maybe 300 kPa, 3 times the atmospheric pressure. The pressures we're going to be dealing with are 3000 kPa. Like, what happens to anything organic at 3000 kPa? This is significant pressure. What happens to like something organic in a tire, right? So we're talking extreme pressures, extreme conditions, and that's why it's really important to get the recovery schemes right, but also the optimizations. And you guys are going to be learning a lot about that. Now, what you see here, historical production, but you can also see the forecast. And all of this mining and the forecast, at least based on kind of the Alberta government slides here, it shows that it kind of plateaus at about 4 million barrels, right? So let's type in the private chat, why do you think the green line plateaus at about 4 million, like the aggregated production, mining and in situ? Why do you think that's happening? I'll give you guys a hint. Um, a pipe will have a certain outer and inner diameter to it, right? Can you flow infinitely something? A pump will have a certain operational capacity of fluids to move through, right? What about surface facilities, guys? What about tanks? Do we have like infinite facilities to store, process, ship? Let's look back at the. You guys remember the slide with the dogs that carried the bitumen? What did they do with that tar? What did they do with it? They treated it. So now you need to treat all of that oil that comes back, right? and you will have steam injection, and that will condense and become water, and you do have sand, right? So I guess what I'm trying to say is that one of the big constraints for the industry through that process that you guys are going to be learning about is that ability to handle stuff at the surface, right? Because nothing here is infinite. And somebody, John, here said you limited by operating capacities, which is correct. But your operating capacity is also a function of flow rate, is function of steam injection capabilities. So you can't generate infinite steam. Like think about this. If let's say you make tea and you have a pot, and let's say you have a guest, one guest. So you have enough from that pot to share with your guest. But what if our entire class is coming to the event? Do you have enough steam? Do you have enough hot water for all of our teas? Maybe you need a bigger pot. Maybe you need two pots. You see what I'm saying? Now, what's the challenge with those facilities now? That if you have very specific amount of facilities, what's the challenge with those now? What do you need to do to make them bigger, larger, maybe more advanced, maybe add more facilities? What do you need to do? You need to spend money. You need something that's called capex, capital expenditure, right? And I think one of the ideas here in this chart is that you simply don't see that investment right now where you can incrementally increase that production. Now, those facilities are not just oil and emulsion kind of treating facilities. Those are also steam generating facilities because remember, we established that we can't just mine with a shovel. We have to inject steam to reduce the viscosity of oil to be produced at the surface. But then we're limited also, we're constrained by the ability to generate that steam. Now, to do that, you need more capex for steam generation capabilities, right? For OTSG. So you need to create that steam. You need to buy, let's say, purchase natural gas, couple the pipe, burn the steam, generate the capability of the steam, build a pipe for that steam to be connected to your pads, inject that steam, right? You see, there's an entire cycle here that's taking place. And then at the back, you need to be able to treat that as well. Okay, so now let's see some prices here. Historically, what's been going on, and important really to connect the dots and understand what we talked about so far. This is Canadian crude oil spot prices for the selected hubs. Here you can see the Western Texas Intermediate, so WTI, and Western Canadian Select, which is the oil that's we're going to be working on optimizing and producing and learning, is trading on. You see differentials, right? You see widening and tightening of those differentials. Again, this is really a function, broader function of the supply demand. Let's say you don't have enough space in the pipe, but you have oversupply, right? Now the differential could change, but in its fundamental kind of basis, the differential really is because we need to transport all of that oil to their unique hubs where they could be treated and continue to be transported back, to transport it down to US, but also the quality of the crude, right? We have crude that is heavier, sour, needs a little bit more kind of money to be spent, ability to kind of to treat it a little bit further, right? So all of that network needs to get paid when the oil gets to the refinery, and then what the refinery is kind of taking in. That's why when you have integrated companies, like for example, one of you mentioned that you did co-op at Cenovus, those type of companies are integrated, so they will have upstream. One of you mentioned as well that you guys are more interested in the upstream kind of project. So those assets will have upstream assets. So for example, in the case of Cenovus, production will be about 800,000 barrels a day, but they're also going to be able to treat refined oil in the United States at I think about 600,000 barrels a day or so. So they're like integrated company, right? So, and the way they do that, they kind of trying to capture that gap there to say, okay, if I'm a refiner, I can take product for cheaper if that gap widens, for example. And this way, I have a hedge towards my upstream operations. You guys Can I understand that concept? One thing you can also see in this chart is the huge volatility. And that volatility, price volatility, has a lot to do with what we already talked about. Think about what's taking place in 2008, 2009. What do you guys think it is? Let's see in the private chat. Why we see a drop from $120 per barrel to 20 on WCS and drop from WTI 130 to 40? What happened in 2008? Housing crisis. That's right. GFC, Great Financial Crisis. What does that impact? Demand. There's a lot of supply, big shock to the system. Obviously, people losing their homes in US, people are being let go. Does that result in more demand or less demand? Less demand, because now you're thinking, oh my God, I was thinking about going to this vacation in Mexico, can't afford it right now, I was let go. Big shock to the system, right? But we see huge restoration of oil prices over the course of, and then we get to 2015. And what happens in 2015? We already talked about that. It was in our second slide, I think, or third slide. I'll give you a hint. We looked at the slopes for oil production in the United States. So that's basically OPEC. We talked about OPEC. He's saying, "Hey, United States, what are you guys doing? You guys like we're going to the moon here with the production. We're not okay with that. We want to compete on global scale with you on prices, on low cost of supply, and therefore we're gonna overflood the market. And therefore, you see this huge drop into 2015 timeframe, oil going from 100, WTI going from 100 to 50. So huge cut. Think about if you're investing in the sector and you make assumptions that you're going to be generating a certain amount of free cash flow, and now this price goes from 100 to 50. So you're a farmer, you used to get paid $100 for your crop, now you get half of that. Is that big impact on your house economics? I would say so. And look at WCS differential is going from $80 to about $25. Now, what's a big learning here for the industry? Like when you see yourself dropping from 80 to 25, and let's say you have debt, what are you learning as an industry? What conclusion are you making? Volatility. But what do you need to do? Like what is essential now for you going forward? Diversify, okay. Maybe integration because now you can take that oil cheaper at the downstream. But I would say you need to be economically competitive, right? You need to be able to survive in an environment where price is volatile, but your operational costs, so everything we talked about, needs to be lower than this price. Because guess what happens if you in 2015 and to 2018, so 3 years, not a month, not two, not a week, for 3 years, if your cost of supply for WCS is more than $20 a barrel, you're not making any money. We're not even talking about investing and capex and everything we talked about as a background to kind of the path forward. Guys, are we okay with extra 10 minutes? I know we said we're going to finish by 2. What does this mean for a new entry level? Sorry, I don't think I understand the question. Okay, let's quickly go. We have 10 minutes and then we'll finish our lecture for today. Because I still want to go into more of the technicals. For us as students, what does it for entry level? Yeah, it was very challenging, right? Like if you're doing co-op and industry is, kind of going, but good news is right now we're not there right now, and we have really good discipline from producers. But and companies went through this experience. So when you enter the sector in the upcoming years, right, you're going to be graduating in April. When you enter the sector, you're looking back and you're like, man, I'm really glad, kind of in a way, in my selfish way, that those events kind of happened, and companies learned how to be low cost of supply companies and went through that experience. That when next time an event like this happens, then we're a little bit more kind of ready for this. And I think that I truly believe that that's how companies are currently positioned, to be very agile, very flexible. There's really good discipline on reducing the amount of debt, right? Because if you were servicing debt in 2016, 2017, and getting WCS at $40 a barrel, that's very challenging, right? You guys agree? Okay. So, and what's more exciting now is that we hear from the government talking a little bit more about increasing production. But look at Alberta's corporate income tax collection, so where the tax money is coming from, and where is the big delta coming from in 2021, 2024 timeframe. Half of it is coming from oil and gas extraction and taxes. It's a very lucrative value proposition for the government to maintaining oil production at these levels, or maybe even increase production, because you can see it's going from $4 billion in tax collection to what, about 8, right? And really a function of the oil price fluctuations. So Alberta government has every incentive for you guys to work in the industry and do a good job to optimize production, maintain production, or slightly increase production, considering we don't have new greenfield projects. And if we have new greenfield projects, this is going higher, considering we have demand for the products, right? Again, we covered that a lot, that it's a little bit complex. You have OPEC, you have OPEC plus, you have a lot of dynamics here that's taking place. Any questions so far, guys? Are we good? All right. So our importance to the United States. So let's look at the slide. We already covered a lot of like what's being imported. As you can see, our biggest customer is United States. But we also, on that, from that graph, at least, do you guys think Canada is important to the United States based on this graph when it comes to heavy oil supply? Yeah, I think so, right? Like you get very little from Venezuela, you get very little from Mexico right now, very little from Colombia. Huge, close to 3 million barrels, right? Heavy oil imports. So, and United States heavy oil production, and I think one of you had mentioned like SAGD happened. Well, unfortunately, SAGD wasn't that important, but they don't really have that type of geology that we have here in Canada, next to Fort McMurray, right? They don't really have those oil sand formations. United States, all of the oil production we talked about, most of it is tight formations, so tight rock formations, which they frack and basically produce lighter oils. And only about 2% of the oil produced is heavy in the United States, and 98% is light medium, which is on the API scale, and maybe next lecture we can learn about that, is less than 20. So that's heavy oil. API scale, less than 20. So current imports close to 3 million barrels a day on the heavy oil side, and mainly imported through Enbridge Mainline to Midwest PADD 2, where a lot of the Canadian non-refineries are also operating. And we talked a little about the integration of oil companies. Okay, I'll be done in like 5 to 10 minutes. Let's quickly cover here about the SAGD technology. So like I said, and we provide a lot of the background to this already, we have very deep, well, relatively to shale, it's not that deep. So if we're at 400 meters, 300 meters, that's actually not that deep, right? Shale could be 2-3 times that distance TVD, like total vertical depth. But what we see here is that can really mine it. So what do? We drill an injector and a producer and inject the steam and produce the emulsion, which is a mixture of the condensed steam, which is water, and oil. Now, this entire next 3-4 months, we're gonna be covering a lot of that. Like we're gonna be talking a lot about this. And the way this technology evolved, it evolved in 1970s with Roger Butler. He worked for Imperial Oil. And he developed this concept of using horizontal pairs of wells and injected steam to develop the deposits for bitumen. Now, we're using this technique now, and the production based on this technique, I would say, is maybe like 1.7, 1.8 million barrels a day between Alberta and Saskatchewan, maybe a little bit more now. And basically, like, this technology was developed in late 70s, but it was really commercialized in early 2000s. So late 90s, early 2000s. And I was very fortunate that one of my previous bosses was one of the pioneers in commercializing this technology, which kind of resulted in me kind of joining the industry and kind of really learning a lot from these pioneers that implemented those technologies, which gave me motivation to also kind of be one of those guys, I guess, in a sense. So very inspiring, right? So my hope is that when you guys join the sector, you're going to find like mentors that going to be inspiring to you, where you're going to be like, okay, I really want to follow your path and be kind of more like you, which was very useful to me. So our oil, the bitumen we're talking about, is very viscous. In its in normal conditions, it's about, I would say, 1 million to 10 million centipoise, and it's really like across all assets, regardless of what asset it is. It's really hockey pucks. It's giant hockey pucks. So if this hockey puck sits deep on the ground, how can I produce it easily, right? And so the solution is you have injector and producer, you inject the steam, reduce the viscosity, and drain everything by gravity. Now, on relative basis, you can see the curve of viscosity reduction based on temperature, right? So when we get to 150 degrees on that scale, you should be flowing like something like an olive oil will flow. If you're at 50 degrees, you flow like molasses. If you are at 20 degrees, 25 degrees, 30 degrees, something like that, it's more kind of like to that ketchup, but it's almost like a no flow, right? Like with ketchup, you almost like need to push it, like you need to make some force, and this thing is not just going to naturally flow unless there is some kind of incentive. Or like a peanut butter, think about peanut butter, right? But the scale is, you can see the curve is not kind of linear, right? It's really a function of temperature. So to create an economic process that where you can inject steam and produce oil and emulsion in an economic way, you have to operate at certain pressure and temperature conditions, right? And so a lot of that science we're going to be covering in this course. So hopefully you kind of see the importance of viscosity. Here's another table of type of liquids relatively to different viscosities. So tomato juice could be 180 centipoise. Mayonnaise could be 5,000, right? Like if you're trying to produce it and not mix it with water or something, very difficult to produce it, right? Window putty, window putty where you like look at this number, you can't really flow that, right? Okay, so this is the same viscosity chart where when we get to 200 degrees, we get to about 10 centipoise. At 100 degrees, we get to maybe 5,000 centipoise, which could be sufficient for flow, but very slow flow, very uneconomic. You'll be waiting, it's like watching paint dry, right? Like it's just not going to flow easily. Okay, so here's a picture of me with the steam chamber. I actually have it here. So I'm going to showcase my, okay, here. So what you see here is injector producer and steam chamber development. What you see in the picture there is half symmetry, right? So half of it, you can see the side of it. We're going to be doing some simulation work where we're going to be analyzing some of those chamber developments. So half symmetry thermal reservoir simulation chamber growth over time is seen in this picture. Explains the low decline over the course of the recovery scheme. And the temperature is red, so roughly 200 degrees. Why is that? Because of the viscosity chart, right? Remember, so everything I'm talking about here is connected. Like all of those slides that tell like broader stories, but they're all interconnected. And the blue is the temperature in situ, which is about 10 to 12 degrees Celsius, which we can't flow. It's a hockey puck, right? So the increase in temperature reduces the viscosity and allows drainage by gravity towards the producing well. Make sense? Okay, so this is my final slide. So I want each and every one of you, and maybe we'll kind of look at the first 5 comments. You see injector producer, injector producer, injector producer. I want each person to, in our private chat here, to tell me what kind of challenge they see as part of this recovery scheme. What could be challenging about this? Like what kind of problems would you have, and what kind of things would you experience if you were? It could be anything. So, and then maybe I'll provide my own. Like if you look at this little diagram here, maybe I'll give you a little hint. What if I introduce a random heterogeneous block in the middle? Non-permeable heterogeneity. What happens to the chamber? Does it look like this? Okay, so here we have a comment: limited radius of the steam non-permeable formation. So I guess the idea here is that you develop only a certain area, right? You can't, you need more wells if you want to expand, right? You can't capture everything. It's very limited to the cavern that you're trying to develop. So would you say the spacing between the wells is important for economics? Yes, very much so. I agree. Okay, next comment. Let's see. So no problems, perfect recovery scheme. Everything is good. We don't need to solve any problems. Think about everything we talked about: money, geology, how deep it is, composition, viscosity, energy intensity. Okay, here we have a comment. Propose a new geometry for the injector and producer. So maybe the idea here is that if you have, let's say, some kind of heterogeneity, you need some kind of unique solution for your wellbore design, maybe completions, right? Okay, so let's get one more, and then I'll give you mine, and I'll kind of tie it back into the project. We still have some people thinking. Okay, maybe not. Okay, so I'll give you mine. Let's say you develop this chamber and you inject steam over time, right? What happens to the cavern? What happens to the reservoir? Is it getting smaller or bigger? Now we talked about it's getting bigger. You're draining fluids and you replacing the oil produced with the injected steam that you inject, right, to that pressure. You guys agree with that? So then what happens after 5, 7, 8, 9, 10 years? I inject steam, but because I developed most of the stuff that's near wellbore and towards the height of the chamber and expanded this laterally, now I need to inject much more steam. But how much oil do I get in return? More or less? Less, right? Because now I kind of rely on that chamber development from the sides to be drained by gravity, which becomes more difficult. So then I will type it in the private chat. The metric that's called SOR, steam to oil ratio, is it increasing or declining? Increasing. Is this good or bad? Bad. Exactly. So we need the lowest SOR possible. Why? Because if I can reduce that steam requirement, produce the same amount of oil, and reallocate the steam to a new well, not only I can cut emissions. I can reduce energy intensity. I can also accelerate oil production rates because now I reallocated the steam somewhere else that's much more productive. But those reservoirs could be coalescing, they could be merging. So now that steam could be migrating from one well to another. So, what is the solution to mitigate the challenge? Is to co-inject NCG, non-condensable gas, something that doesn't condense like steam, able to maintain pressure, maintain oil production, and reduce the SOR. See? And that's what our project is going to be about. It's going to be about learning about these assets, introducing NCG, the timing of NCG, building reservoir simulation models to better understand the dynamic, the timing, the integration, the geology, the challenges. And our entire attempt here is to really reduce SOR. That's what this project is all about. Make sense, guys? You see why it's useful? So we started from total oil demand, Canadian role, bitumen production within the Canadian production, optimization of Canadian production. We went down to the reservoir level production and technology integration to optimize SAGD operations. This is what it's all about, guys. So I'm gonna upload this on YouTube. Again, you can rewatch it, better understand the dynamics. Next week we're gonna meet probably same time. Does that work? Yeah, and then we can kind of gonna go over more stuff. Now, what I'm asking the teams to do, at the end, you will have a big report, right? So for next week, start working about doing research, not write anything, but start doing research as a team about SAGD assets. Like where are they? Where are they located? What are the companies that running those assets, right? It's as easy as Googling NCG co-injection, SAGD, something. Start getting that background. So then when we go to lecture 2, we can start talking a little bit more tactically about the next steps and kind of growing our project as we advance further. Okay, guys? Okay, so hopefully you guys happy. Thanks so much for listening to this presentation. Here we have a question. Is there specific geographical area or companies we're focusing on? Well, we covered them already, right? So we talked, if I go to the previous slide. So the area, Western Canadian Sedimentary Basin, right? So Alberta, Saskatchewan. And all of the companies that operate here that produce bitumen in situ, those are SAGD companies. It's very easy to Google and just see who they are. We don't have that many, so it's going to be very easy for you to identify. All right. And we had mentioned some of those companies in this discussion already. One of you interned there last year, remember? All right. Thank you, guys. Message me, send me an email if you have any questions. And again, really appreciate the opportunity to provide value to you during your petroleum engineering capstone program. And yeah, let's go from there. Okay. Yeah, you're welcome. Thank you. We'll be joining via stream. Yeah, next week. Yeah, so I hibernating on LinkedIn right now. We talked about this why, but I'll be back soon. So, all right. Anything else? Okay, thank you, friends. All the best.